Have you ever stopped to think, I mean, really think, about what's going on inside your computer when you, say, click an icon or open an app?
It just happens, right?
Yeah.
Feels instant,
Right.
like magic. But behind that easy experience, there's this incredible hidden orchestration. Today, we're pulling back the curtain on these unsung heroes of computing. Operating systems, they're the master conductors making everything work, managing your hardware, your software, your whole digital life, really. So our mission is to do a deep dive. We're looking at the core functions, the hidden complexities of operating systems. We've got foundational lecture notes, research, and we want to give you a shortcut to understanding the heart of your digital world. Okay, let's just jump right in. What exactly is an operating system? I mean, the definition says it's a program that acts as an intermediary between a user and the computer hardware. Sounds simple, but what does that really mean in practice?
It's exactly that, fundamentally. Think of the OS as this sophisticated collection of system programs. They all work together, controlling the whole computer system. It's not just one thing. It's a suite. And you've used them, maybe without thinking about it too much. Windows, macOS, Linux, Android, iOS. They're all designed at their core to manage that underlying hardware.
Right. And from our side, as users, the goals seem pretty obvious. We want to run our stuff, solve problems, have a computer that's, easy to use. But from the system's perspective, it's different, isn't it? It's about using that hardware efficiently, getting the most bang for the buck.
Exactly. Efficiency is key from the system's view. If you break down any computer system, you basically got four core components interacting. First, the hardware. That's your CPU, your memory, your I/O devices, the raw computing power. Then, the operating system itself. It controls and coordinates how that hardware gets used, who gets what, when. Third, the applications programs, your browser, your word processor, games. They define how those resources actually get used to solve your problems.
Yeah.
And finally, the users. That could be people like us, machines, or even other computers needing something.
Hardware, OS, apps, and us.
Got it. The OS is the glue. But how else can we define its role, beyond just being an intermediary? Well, there are a few key ways to look at it. It's definitely a resource allocator. Its job is to manage and hand out all the computer's resources, CPU time, memory space, disk access, everything, fairly and efficiently. It's also a control program. It controls how user programs execute, oversees the I/O devices, basically prevents errors and improper use, keeps things orderly. And maybe the most fundamental part is the kernel. That's the core. It's often called the one program running at all times.
The kernel, right, that's the bit that talks directly to the hardware.
Pretty much. It interacts with device drivers,
Yeah.
system files, those DLL files you sometimes see. It's the active heart of the OS.
Mhm.
And then there's the shell. That's the command interpreter. It's how you or your applications actually talk to the OS. Translates your clicks or typed commands into actions the kernel can understand.
So it's this constant juggling act. On one side, it's making things easy and useful for us users. And on the other, it's this strict manager, keeping everything in line, controlling access, preventing chaos. It really is an unsung hero. Okay, so that's what it is. But what does the OS actually do? It's clearly not just sitting there. It's managing things constantly. What are its main jobs?
Right, it's incredibly busy. The OS was performing this constant symphony of management tasks. First up, a really big one. Process management. Think of a process as simply a program in execution. When your browser is running, that's a process. Your game, that's another process. Yep. And these processes need stuff. They need CPU time, they need memory, access to files, I/O devices. The OS is responsible for creating them, deleting them when they're done, pausing them, resuming them, and, importantly, providing ways for them to communicate and synchronize with each other. Without that, it'd be chaos.
Makes sense. What else?
Then there's main memory management, your RAM. Think of it like a big, fast, but temporary workspace. Its volatile storage power goes off, it's all gone.
Right.
So the OS acts like a meticulous librarian for this memory. It tracks who's using what part, decides which processes or parts of processes get loaded into memory when there's space, and handles allocating and deallocating that space as programs come and go. Crucial for preventing programs from crashing into each other.
Like assigning shelves in the library.
Yeah.
Exactly. Then there's file management. A file is just a collection of related information, documents, pictures, applications themselves. The OS handles everything related to files, creating them, deleting them, opening, closing, reading, writing. It also maps these logical files onto your physical storage, like your hard drive or SSD, and handles things like backup.
Okay, so processes, memory, files. What about talking to the outside world? Keyboards, printers?
That's I/O system management. Input-output. It oversees all those operations. It involves things like buffering data, having a standard way to talk to different devices. the device driver interface, and specific drivers for each piece of hardware. Tied into that is secondary storage management. Because main memory is volatile and relatively small, you need permanent storage, usually disks, hard drives, or SSDs. The OS manages the free space on these disks, decides where to put files, storage allocation, and schedules the disk operations efficiently so you're not waiting forever.
And keeping everything safe.
Absolutely. That's the protection system. It's all about controlling access. Who or which program, which user can access which resources. It needs to distinguish authorized from unauthorized use, specify the controls, and enforce them rigorously. Security and privacy depend on this.
It's an incredible amount of coordination. And, thinking about it, the history of OSs is really a story of trying to get more out of the hardware, right? Making things faster, more interactive.
Absolutely. It's a journey driven by efficiency and usability. In the early days, with mainframe systems, computers were hugely expensive. The main goal was just keeping the CPU busy. Operators would literally batch similar jobs together to cut down on setup time. This led to the first simple OS components like resident monitors just to automate loading the next job.
Just basic automation.
Pretty much. This evolved into proper batch processing operating systems. They'd group jobs with similar needs and run them one after the other. The OS was basically just a scheduler, often using simple priorities.
But still, one job at a time.
Right. The big problem was the CPU sitting idle whenever a job waited for slow I/O, like reading tape. That waste led to multi-programming operating systems. This was a huge leap. The idea was to keep several jobs in memory at once. If one job had to wait for I/O, the OS would quickly switch the CPU to another job that was ready to run.
So keeping the CPU busy all the time.
Exactly. As long as there was some job ready to compute, the CPU was never idle. Massive increase in utilization.
And then making it interactive.
That was the next logical step. Time sharing or multitasking operating systems. It's an extension of multi-programming, but with much faster switching between jobs. This created the illusion that multiple users could share the same system simultaneously, each interacting with their own running programs in real time. This is where things like virtual memory became really important too.
And as hardware got more powerful, like multiple CPUs in one machine.
Then we needed multiprocessor operating systems, sometimes called parallel or tightly coupled systems. These manage systems with more than one processor working together, sharing memory and peripherals. The advantages are significant. Increased throughput, more work done faster. Economy of scale, sharing resources is cheaper. And increased reliability.
Reliability. How so?
Well, if one processor fails, the others can often take over its tasks. It's called graceful degradation or fault tolerance. The whole system doesn't crash. These can be symmetric, SMP, where all processors are peers running the same OS, or asymmetric, with the master-slave setup.
Okay. And networking computers together.
Led to distributed operating systems. Here you have multiple independent computers, each with its own OS, processor, and memory, connected by a network. But their OSs cooperate to manage the collective resources of the network. This allows for things like sharing files across machines, speeding up computations by distributing the load, and enhance reliability through redundancy.
Then we get to the computers most of us use daily.
Right, desktop systems or personal computers. Early ones like MS-DOS were pretty basic single user, no multitasking. But they evolved rapidly. Systems like the Apple Macintosh and later Windows brought in sophisticated GUIs, virtual memory, multitasking, making powerful computing accessible and user-friendly.
And there's one more type you mentioned for very specific needs.
Yes, real-time operating systems, RTOS. These are crucial for systems where timing is absolutely critical. Embedded controllers, industrial robots, medical devices, spacecraft. They have fixed time constraints. And there's a key distinction. Hard real-time systems guarantee that critical tasks finish on time. Missing a deadline is unacceptable, potentially catastrophic. Think flight control systems. Soft real-time systems prioritize critical tasks, but offer fewer guarantees. A missed deadline might degrade performance, but isn't a total failure. Useful for things like streaming media.
It really does sound like the OS is our digital butler, or maybe concierge, providing all these essential services, often without us even noticing.
That's a great analogy. The OS provides a whole suite of services. Some are directly for user convenience, like program execution, providing the environment, loading the program, managing its execution, handling all I/O operations, getting input from your keyboard, sending output to the screen or printer, file system manipulation, letting you create, delete, read, write, search files and directories, communications, allowing different processes to exchange information, maybe through shared memory or network messages, and crucially, error detection. The OS is constantly monitoring for hardware or software errors, trying to prevent them from causing bigger problems.
Okay, so those are for us. What about for the system itself?
Right, there are services focused on ensuring efficient system operation. Resource allocation is key, distributing resources like CPU cycles, memory, devices fairly among multiple users or jobs running concurrently. Accounting, keeping track of which users use how much and what kinds of resources. Useful for system tuning or even billing on large systems. And protection and security, ensuring that access to resources is controlled, preventing users or programs from interfering with each other, authentication like passwords, all that jazz.
So if the OS provides all this, how do our programs actually request these services? They can't just grab the hardware themselves, right?
Exactly. That would be chaos.
Yeah.
They use system calls. A system call is the mechanism programs use to request a service from the operating system's kernel. Think of it as the official way for a user program to ask the OS to do something privileged, something it isn't allowed to do directly, like accessing a file or starting another program.
Knocking on the kernel's door and asking politely.
Precisely. There are different types of system calls for different needs. Process control, like ending a program, creating a new one. File management, create, delete, open, read, write files. Device management, requesting access to a printer, releasing it. Also, information maintenance, getting the times, system settings, and communications, creating network connections, sending, receiving messages. They're the bridge between user space and kernel space.
Okay, let's talk about that CPU again. The OS makes it feel like it's doing dozens of things at once, even if there's only one CPU core. How does it manage that juggling act, this CPU scheduling?
Right, CPU scheduling is fundamental, especially for multi-programming. The goal is maximum CPU utilization, keep that processor working. Processes typically alternate between executing CPU instructions, a CPU burst, and waiting for I/O, an I/O burst. It's this cycle.
Okay.
The CPU scheduler is the part of the OS that looks at all the processes in memory that are ready to run and picks one to give the CPU to. These decisions can be non-preemptive, meaning a process keeps the CPU until it voluntarily gives it up, finishes its CPU burst, or waits for I/O. Or preemptive, where the OS can actually take the CPU away from a running process, maybe because its time slice ran out, or a higher priority process just became ready.
And the actual switch itself.
That's done by the dispatcher. It's the module that gives control of the CPU to the process selected by the scheduler. This involves switching context, switching to user mode, and jumping to the right spot in the program to resume execution. It has to be fast.
So how do we judge if the scheduler is doing a good job? What are the metrics?
There are several scheduling criteria used to measure performance. From the system's point of view, you want high CPU utilization, keep it busy, and high throughput, how many processes complete per unit time. From the user's perspective, you want low turnaround time, total time for a process to complete from start to finish, low waiting time, how long processes spend waiting in the ready queue not running, and especially for interactive systems, low response time, time from command input until the first response appears, not the whole job finishing. You want it to feel responsive. The goal is usually to optimize the average, but sometimes minimizing the maximum or variance is important too.
Okay, so how does the OS actually decide who goes next? What are the different strategies or algorithms?
There's several classic algorithms. The simplest is first come, first served, FCFS.
Sounds straightforward.
It is. It's just like a queue at the store. Processes get the CPU in the order they arrive in the ready queue, managed with a simple FIFO queue. But it has a big problem, the convoy effect. If a long CPU-bound process gets the CPU, all the short I/O-bound processes behind it have to wait, even if they just need a tiny bit of CPU time.
Ah, like being stuck behind someone with a huge shopping cart when you just have milk.
Exactly. It leads to poor average waiting times and lower utilization of I/O devices. Because it's non-preemptive, it's especially bad for interactive time-sharing systems.
So what's better?
Well, theoretically, shortest job first, SJF, is optimal for minimizing average waiting time. The idea is simple. Give the CPU to the process that has the smallest next CPU burst.
Smallest next burst. How do you know that?
Ah, that's the catch. You can't perfectly predict the future. So true SJF is impossible to implement. It's often approximated by predicting the next burst based on previous ones. SJF can be non-preemptive or preemptive. The preemptive version is called shortest remaining time first. If a new process arrives with a shorter remaining time than the currently running one, the OS preempts the current one.
Okay, so FCFS is simple but potentially unfair. SJF is optimal but impractical. What else?
Priority scheduling. Each process gets a priority number, and the CPU goes to the process with the highest priority. Simple FCFS is used for ties. SJF can actually be seen as a special case of priority scheduling, where the priority is based on the predicted next CPU burst length.
Does priority have downsides?
Yes, the main one is starvation or indefinite blocking. Low-priority processes might never get the CPU if there's a steady supply of high-priority ones. A common solution is aging, gradually increasing the priority of processes that wait for a long time. Eventually, they'll get a turn.
That seems fair. And what about the one that gives that smooth multitasking feel on desktops?
That's round robin, RR. It's designed specifically for time-sharing systems. It's preemptive. Each process gets a small unit of CPU time called a time quantum or time slice, typically 10 to 100 milliseconds. When a process gets the CPU, it runs for up to one time quantum. If it's still running at the end, the OS preempts it, puts it at the end of the ready queue, which is treated like a circular queue, and gives the CPU to the next process in line.
So everyone gets a small turn frequently.
Exactly. If the time quantum is small, it creates the illusion that all processes are running concurrently, each on its own slower processor. It optimizes response time, which is key for interactivity.
It really is clever how a tiny slice of time makes such a difference. Now, thinking about modern apps, they often do lots of things at once, right? Downloading, displaying, checking spelling. How does the OS handle that within a single application? Is it more than just separate processes?
Yes, absolutely. This is where threads come in. You can think of a thread as a lightweight process, or LWP. It's the basic unit of CPU utilization. A thread has its own thread ID, program counter, register set, and stack.
Okay, sounds like a process so far.
But here's the key difference. Multiple threads within the same process share the process's code section, data section, and other OS resources, like open files and signals. A traditional heavyweight process has just one thread of control. A multi-threaded process can do multiple tasks concurrently, sharing resources easily.
So why go to the trouble of using threads? What's the payoff?
There are huge motivations and benefits. Think about your web browser again. One thread could be displaying the page you're looking at, while another thread in the background is downloading images or data for a link you might click soon.
Right, so things don't freeze up.
Exactly. Or a word processor. One thread handles your typing and displaying text, another handles background spell checking, maybe a third handles auto-saving. For something like a busy web server, creating a whole new heavyweight process for every single client request would be really inefficient. Instead, it can create a lightweight thread for each request. Much faster, less overhead.
So what are the main advantages then?
First, responsiveness. If one thread in a program blocks, like waiting for network data, other threads in the same program can keep running. The application doesn't freeze, it stays interactive. Second, resource sharing. Threads share memory and resources of their parent process by default. This makes it super easy for different parts of the same program to work on the same data. Third, economy. Creating and switching between threads is way cheaper and faster than creating and switching processes. Because they share so much, there's less setup and teardown involved. Our source mentioned Solaris 2, where creating a process was like 30 times slower than creating a thread.
Wow, 30 times.
Yeah, and context switching 5 times slower for processes. Big difference. And finally, utilization of multi-processor architectures. This is huge today. A single-threaded process can only run on one CPU core at a time. But a multi-threaded process can run its threads in parallel on multiple cores, getting a massive speed up.
Okay, so just to nail it down, what's the core operational difference between a process and a thread?
It really boils down to independence versus sharing, and the resulting overhead. Processes are largely independent. They generally don't share memory easily. They take more time and resources to create, terminate, and switch between. Inter-process communication usually needs explicit OS help via system calls.
Okay.
Threads, on the other hand, are lightweight. They share memory and resources within their process. They're much faster to create, terminate, and switch between. Communication between threads in the same process is often trivial because they share data directly. They use fewer resources overall.
Got it. Lightweight, shared, fast. Processes are heavyweight, isolated, slower. Now, with all these processes and threads potentially using the same data or devices, how does the OS stop them from tripping over each other? How does it prevent, say, two threads from trying to update the same bank balance at the exact same time and messing it up?
That's a critical problem. And it leads us to process synchronization. The scenario you described is called a race condition. It happens when multiple processes or threads access and manipulate shared data concurrently, and the final result depends on the particular order, the race, of how their operations interleave. It often leads to corrupted data.
Okay, so how do we prevent that race?
We need mechanisms to control access to shared resources. A classic example illustrating this is the producer-consumer problem. You have a producer process creating data and putting it into a shared buffer, and a consumer process taking data out. You need synchronization to make sure the producer doesn't try to add data to a full buffer and the consumer doesn't try to remove data from an empty buffer. They have to coordinate.
Right. And the part of the code that accesses the shared stuff?
That's called the critical section. It's the segment of code where a process or thread accesses shared resources, like shared variables. The fundamental challenge is ensuring mutual exclusion. Only one process can be executing in its critical section at any given time. If one process is updating the shared data, all others wanting to do the same must wait.
So mutual exclusion is key. Are there other requirements for a good solution?
Yes. A solution to the critical section problem must satisfy three conditions. 1, mutual exclusion, as we said. Only one process in the critical section at once. 2, progress. If no process is in its critical section, and some processes want to enter, the decision of which process gets to enter next cannot be postponed indefinitely. Things have to keep moving. 3, bounded waiting. There must be a limit on the number of times other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. Basically, no process should wait forever.
Okay, mutual exclusion, progress, bounded waiting. How does the OS actually achieve this?
Various tools are used. One classic synchronization tool is the semaphore. You can think of it as an integer variable that's only accessed through two special atomic operations: wait, often called P, and signal, often called V. A simple binary semaphore or mutex can act like a lock. Before entering the critical section, a process calls wait. If the lock is free, semaphore is 1, it acquires the lock, sets semaphore to 0, and enters. If the lock is busy, semaphore is 0, the process waits. When it leaves the critical section, it calls signal, releasing the lock, sets semaphore back to 1.
So it controls access, like a key for the critical section room.
Exactly. Semaphores can also be used for more complex coordination, like making sure one process waits for another to finish a certain task.
But what happens if things go really wrong? What if processes end up waiting for each other in a way that nobody can proceed? The ultimate traffic jam.
Ah, that's a deadlock. A set of processes is deadlocked if each process in the set is waiting for an event that can be caused by only another process in the set. Imagine process 1 has resource A, say a hard disk, and needs resource B, a printer. But process 2 has resource B, the printer, and needs resource A, the hard disk. Yeah? Process 1 waits for process 2 to release B. Process 2 waits for process 1 to release A. Neither can proceed. They're stuck in a deadly embrace. That's a deadlock.
Okay, that's a clear example. So what conditions have to be met for this kind of situation to even arise?
There are 4 necessary conditions for deadlock identified by Kaufman back in 1971. All 4 must hold simultaneously for a deadlock to occur. 1, mutual exclusion. At least one resource involved must be held in a non-shareable mode. Only one process can use it at a time, like our printer example.
Okay.
2, hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently held by other processes. Process 1 holds A, waits for B. 3, no preemption. Resources cannot be forcefully taken away from a process holding them. They must be released voluntarily by the process. We can't just snatch the printer from process 2.
Makes sense.
4, circular wait. There must exist a set of waiting processes, P0, P1 line, such that P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, Pn is waiting for a resource held by P0. That circular chain is key.
All 4 have to happen at the same time.
Yes. If even one of these conditions isn't met, a deadlock cannot occur.
Okay, knowing the conditions is one thing, but how does an OS actually deal with deadlocks? Can it prevent them? Fix them?
There are basically 4 approaches. First, deadlock prevention. This strategy ensures that at least one of the 4 necessary conditions can never hold. For example, you might require processes to request all needed resources at the very beginning, breaking the hold and wait condition. Or you could impose a total ordering of all resource types, forcing processes to request resources in a specific order, which breaks the circular wait condition.
So design the system rules to make deadlock impossible.
All right. Second, deadlock avoidance. This is more dynamic. The OS requires processes to declare the maximum resources they might need in advance. Then, whenever a process requests a resource, the OS checks if granting the request would leave the system in a safe state, meaning there's some sequence in which all processes can finish. If granting the request could lead to an unsafe state and potentially deadlock, the process has to wait. The banker's algorithm is a famous example of this.
Checking the future, basically.
In a way, yes, it's proactive. Third, deadlock detection and recovery. This approach allows the system to enter a deadlock state, detects it, and then recovers. Detection involves algorithms that check the system state for circular weights. If a deadlock is detected, recovery might involve process termination, either aborting all deadlocked processes, simple but costly and lost work, or aborting one at a time until the deadlock cycle is broken, or resource preemption. Forcibly take some resources away from deadlocked processes, victim selection is tricky, and give them to others. This often requires rolling back the victim process to some earlier safe state, which is complex.
Okay, prevention, avoidance, detection, recovery. What's the fourth?
The fourth approach is often called the ostrich approach.
Chuckles, let me guess.
You got it. Just ignore the problem altogether, pretend deadlocks don't happen.
Seriously, is that ever a good idea?
It's actually surprisingly common in many general-purpose operating systems like Unix and Windows. The reasoning is that deadlocks are relatively rare in well-behaved systems, and the overhead of prevention, avoidance, or even detection recovery mechanisms might be higher than the cost of the occasional deadlock. If one happens, the user might just have to reboot.
A calculated risk, then.
Pretty much.
Yeah.
If deadlocks are extremely infrequent, sometimes the simplest solution is deemed acceptable.
Okay, let's shift gears a bit. Talk about memory management again. It often feels like magic how computers can run huge programs, sometimes bigger than the actual physical RAM. How does that illusion work?
That's the magic of virtual memory, built upon techniques like paging. First, remember that in multi-programming, the OS dynamically subdivides memory. And there's this concept of address binding linking program instructions in data to actual memory addresses. This binding can happen at compile time, load time, or, most flexibly, at execution time. Execution time binding allows a process to be moved around in memory during its execution, which requires hardware support. This leads to the distinction between the logical address, or virtual address, generated by the CPU, and the physical address, which is the actual address seen by the memory hardware. The Memory Management Unit, MMU, is the hardware that does this translation on the fly.
Okay, so logical versus physical addresses. How does the OS make the logical space seem huge?
Primarily through paging. The basic idea is to break physical memory into fixed-size blocks called frames and break logical memory, the program's view, into blocks of the same size called pages. When a program runs, its pages are loaded into available frames in physical memory. Crucially, these frames do not need to be contiguous. A program's pages can be scattered all over physical RAM.
Like chapters of a book scattered on different library shelves.
Exactly. And the OS keeps a page table for each process, which acts like an index, telling it which frame holds which page. So when the CPU generates a logical address, page number plus offset within the page, the MMU uses the page table to find the corresponding frame number, combines that with the offset, and gets the physical address.
That sounds like it could be slow, looking things up in a table all the time.
It could be, which is why there's hardware help. The translation look-aside buffer, TLB. It's a small, very fast hardware cache that stores recent page-to-frame translations. If the needed translation is in the TLB, a TLB hit, the physical address is generated super fast. If not a TLB miss, the system has to look it up in the full page table in memory, slower, and then it usually adds that translation to the TLB, hoping it'll be needed again soon.
Okay, TLB speeds things up. And this enables the big trick. Virtual memory.
Precisely. Virtual memory is a technique that allows the execution of processes that may not be completely in memory. It separates the user's logical memory view from the physical memory reality. This means a program can have a huge logical address space, say gigabytes or terabytes, even if the machine only has a few gigabytes of physical RAM.
How? Where do the other parts of the program live?
On disk, typically in a swap file or partition. The beauty is that only the parts of the program actively being used need to be in physical memory at any given moment. This allows it to run more programs concurrently than could fit entirely in RAM, simplifies programming, developers don't need complex overlay techniques, and makes process creation faster.
So how does the OS decide which parts to bring into RAM?
That's usually done using demand paging. It's a lazy approach.
Yeah.
A page is never brought into memory from disk unless it's actually needed. When a process tries to access a page that's not currently in memory, it's marked as invalid in the page table. This triggers a page fault interrupt.
An error.
Not really an error, more like a signal to the OS. The OS handles the page fault. It checks if the access was valid, just to a page not currently in memory, finds a free frame in RAM, schedules a disk operation to read the required page from disk into that frame, updates the page table to show the page is now valid and in memory, and then restarts the instruction that caused the fault.
So it brings pages in only when absolutely necessary. Pure demand paging.
Exactly. Minimizes I/O and memory usage.
But what if there are no free frames when a page fault happens? All the RAM is full.
Ah, good question. That's where page replacement comes in. If there are no free frames, the OS has to choose an existing page in memory, a victim frame, to swap out to disk to make room for the new page coming in.
Choosing a victim, how does it pick? Are there different strategies?
Yes, there are several page replacement algorithms. One is first in, first out, FIFO. Simple. Replace the page that has been in memory the longest. Like the FCFS scheduling, it's easy to implement, but not always great performance. And this is where you can hit Belady's anomaly. Counterintuitively, for some page reference patterns, giving FIFO more memory frames can actually increase the number of page faults. More memory, worse performance. It's bizarre, but true for FIFO.
Weird. So FIFO isn't ideal. What else?
Well, the theoretical best is the optimal page replacement algorithm, OPT or MIN, that says replace a page that will not be used for the longest period of time in the future. This guarantees the lowest possible page fault rate and never suffers from Belady's anomaly.
But you can't predict the future.
Exactly. So OPT is impossible to implement perfectly. It's mainly used as a benchmark to compare other algorithms against.
So what's a practical good algorithm?
A very common and effective one is least recently used, LRU. It works on the assumption that pages used recently are likely to be used again soon, and pages not used for a while are less likely to be needed. So LRU replaces the page that has not been used for the longest amount of time. It approximates OPT pretty well in practice, though implementing it efficiently requires hardware support, like reference bits, or clever software techniques, like counters or stacks.
Okay, LRU makes sense. Is there a danger of swapping pages in and out too much?
Yes, definitely. That leads to a condition called thrashing. Thrashing happens when a system spends far more time paging, swapping pages between memory and disk, than actually executing instructions. The CPU utilization plummets because processes are constantly waiting for pages to be loaded.
It's just churning memory instead of doing work.
Precisely. And the OS might mistakenly think it needs to increase the degree of multi-programming, let more processes run, because CPU utilization is low, which just makes the thrashing worse because there's even more competition for the limited memory frames. It's a vicious cycle.
Got it. Avoid thrashing. Okay, let's move from managing volatile memory to managing permanent storage. How does the OS organize all our files, documents, photos, apps so we can actually find them?
This is the domain of file systems. At its core is the file concept. A file is basically a collection of related information that is recorded on secondary storage. From the user's view, it's the smallest logical chunk of storage. Files often fit into a hierarchy, a field, like a name, a record, info about one person, a file, collection of records like all employees, maybe even a database-related files.
And the OS keeps track of info about the files.
Yes, file attributes. Things like its name, a unique identifier, its type, .txt, .exe, .mp3, location, where it is on disk, size, protection info, who can read, write, execute, and timestamps, creation, last modification, last access. The OS provides standard file operations. Creating a file, finding space, making a directory entry, writing, keeping track of where the next write should go, reading, tracking the next read position, repositioning within a file, like seeking in a video file, often called lseek, deleting, releasing space, removing the directory entry, truncating, keeping attributes, but erasing content.
How do we access the data inside the files? Is it always just start to finish?
Not necessarily. There are different access methods. Sequential access is the simplest. Information is processed in order, one piece after another. Think reading a text file or listening to an audio stream. The OS maintains a pointer to the current position, which advances automatically. But direct access, or random access, is also common. Here, the file is viewed as a numbered sequence of logical records, or blocks, and you can read or write any record directly, without going through the ones before it. Think of accessing records in a database. You want to jump straight to customer #12344, not read through 1233 others first. This requires the underlying storage, like a disk, to support random access.
With potentially thousands, even millions of files, how does the OS keep track of where everything is? How is it organized?
That's the job of the directory structure. Early systems used a single-level directory, just one big directory for all files. Simple, but quickly became a nightmare with many files or multiple users named collisions.
I can imagine.
So the next step was a two-level directory. Each user gets their own private directory, user file directory, or UFD. A master file directory, MFD, points to each user's UFD. Now, different users can have files with the same name, e.g. project.txt, without conflict, because they're in different UFDs.
Better, but still limited.
Yes. Most modern systems use tree-structured directories. This is the hierarchical structure you're familiar with. Directories can contain files and other directories, subdirectories, creating a tree. You navigate using paths, like home user documents report.dfc, much more organized.
Can you share directories or files between different parts of the tree?
Yes, that leads to acyclic graph directories. These allow directories to have shared subdirectories and files. It's achieved using links or shortcuts. The same file or directory can appear in multiple locations in the directory structure. An important point. A shared file via a link is not the same as having two separate copies. If you modify the linked file through one path, the changes are visible through all other paths pointing to it. With copies, changes are independent.
Okay, so that's the logical organization. Where do these files actually live physically? On disks, right? How does the OS manage that physical space?
Right, secondary storage structure, primarily magnetic disks or SSDs. Disks provide the bulk storage. Physically, a magnetic disk has platters coated with magnetic material rotating at high speed. Read-write heads on a movable arm access the data. The surface is divided into concentric circles called tracks, and each track is split into sectors. A cylinder is a set of all tracks at the same arm position across all platters. Performance depends on transfer rate, how fast data moves once the head is positioned, and positioning time, or random access time, which is the sum of seek time, moving the arm to the right cylinder, and rotational latency, waiting for the desired sector to spin under the head.
And the OS sees this complex physical structure.
Usually the OS abstracts it. Modern disks are typically addressed as just a large one-dimensional array of logical blocks, where each logical block maps to a physical sector. The disk controller handles the translation.
So when the OS needs to read or write blocks, does it just process requests in the order they arrive, or is it smarter than that?
It's usually smarter. That's disk scheduling. Because seek time is often a dominant factor in disk performance, the OS tries to schedule the order of disk I/O requests to minimize total seek time and improve throughput.
How does it do that? What are the algorithms?
FZFS, first come, first served, is the simplest. Again, fair but potentially inefficient if requests are scattered all over the disk, causing lots of seeking back and forth. SSTF, shortest seek time first, selects the request that requires the minimum arm movement from its current position. It goes to the closest pending request next. Reduces seek time significantly, but can lead to starvation for requests far from the current head position.
Like scan and C-scan? What are those?
Scan, also sometimes called the elevator algorithm, works like this. The disk arm starts at one end of the disk and moves towards the other end, servicing requests in its path. When it reaches the other end, it reverses direction and sweeps back. C-scan, circular scan, is similar, but when the arm reaches one end, it immediately returns to the beginning of the disk without servicing any requests on the return trip, then starts sweeping across again. This provides a more uniform waiting time than scan. Those are just practical optimizations of scan. Instead of going all the way to the end of the disk, the arm only goes as far as the last request in its current direction, then reverses immediately, avoids unnecessary travel.
Okay. And what about making disks more reliable? What's RAID?
RAID stands for Redundant Array of Inexpensive Disks. It's a set of techniques to use multiple physical disks working together to improve performance, reliability, or both. It treats the array of disks as a single logical drive. Data is often distributed across the disks using striping, improves performance. Redundancy is added, like parity information or mirroring, so that if one disk fails, the data can still be recovered from the remaining disks. Common levels include RAID 0, striping only, no redundancy, fast but unsafe; RAID 1, mirroring, high reliability, expensive; and RAID 5, striping with distributed parity, good balance of performance, capacity, and reliability. All right. Last big piece, the I/O system itself. How does the OS manage communication with all the external devices? Keyboards, mice, networks, printers, the connection to the outside world. The I/O system is fundamental. The OS manages and controls all these I/O operations and devices. Devices connect to the computer via connection points like a bus, a set of shared wires, or maybe a daisy chain. Each device usually has a controller, the electronics that operate the device, and interface with the bus or port. The CPU interacts with the controller through an I/O port, which typically has registers for status. Is the device busy? Control, tell the device to start. Data in, read data from device, and data out, write data to device. Devices fall into broad categories. Human readable for user interaction, like keyboards, monitors, printers. Machine readable for communicating with electronic equipment, like disks, sensors, controllers. And communication for remote devices like modems, network cards.
How does the CPU actually talk to these controllers efficiently? It can't just sit and wait for a slow printer, can it?
No, that would be terribly inefficient. There are three main I/O techniques. Programmed I/O is the simplest. The CPU issues a command to the controller, then enters the loop, constantly checking the controller's status until the operation is complete. Busy waiting. Wastes a lot of CPU time.
Not ideal.
Definitely not. Better is interrupt-driven I/O. The CPU issues the command and then goes off to do other work. When the controller finishes its operation, it sends an interrupt signal to the CPU. The CPU finishes its current instruction, saves its state, and jumps to a special routine called an interrupt handler, part of the OS, to process the completed I/O. This is far more efficient. As we said, an operating system is interrupt-driven. It reacts to events like I/O completion.
Okay, interrupts are better. Is there anything even more efficient for large data transfers?
Yes, for high-speed devices like disks or networks, direct memory access, DMA, is used. With DMA, the CPU tells a special DMA controller what data to transfer, where it is in device memory, a buffer in the controller, where it goes in main memory, and how much data to transfer. Then the DMA controller transfers the entire block of data directly between the device controller's buffer and main memory, without involving the CPU for each byte or word.
The CPU is completely bypassed.
For the actual data transfer, yes. The DMA controller sends just one interrupt to the CPU when the entire block transfer is complete, instead of one interrupt per byte as an interrupt-driven I/O for slow devices. Huge reduction in CPU overhead for bulk transfers.
Makes sense. And the OS provides services on top of this.
Yes, the kernel I/O subsystem provides services that make I/O easier and more efficient for applications. Things like I/O scheduling, like disk scheduling, but can apply to other shared devices. Buffering, using memory areas to hold data temporarily during transfers, coping with speed differences or transfer size mismatches. Caching, keeping copies of frequently accessed disk data in faster main memory. Spooling, buffering output for devices like printers that can't handle interleaved data from multiple jobs. And device reservation, allowing a process to get exclusive access to a device.
Wow. So even a simple action, like saving a file, involves this incredibly complex journey through system calls, scheduling, memory management, I/O handling, maybe DMA. It's amazing. It feels so instant. We've really covered a lot of ground today, from the basic idea of an OS as an intermediary through its core jobs, managing processes, memory, files, I/O. We looked at how OSs evolved to handle multitasking, multiple processors, distributed systems. We dug into system calls, CPU scheduling strategies, the efficiency of threads, the dangers of race conditions and deadlocks, the magic of virtual memory and paging, and finally, how it all connects to the physical world through file systems and I/O management.
It really is an astonishing piece of software engineering. The OS does so much heavy lifting, abstracting away the messy hardware details, managing complex resources fairly and efficiently, and providing that stable platform so applications and users can actually get things done. All happening constantly, mostly invisibly, just making things work.
Absolutely. So next time you fire up your computer, open a browser, switch between apps, save that document. Just take a moment to appreciate the intricate dance happening beneath the surface, that silent, complex choreography orchestrated by your operating system. It's what makes your digital world spin. And thinking about the future, with technology evolving so fast, AI, massive cloud systems, the Internet of Things, what do you think are the next big challenges? What innovations will operating systems need to keep everything running smoothly, securely, and efficiently in the years to come? Something to ponder.